In this next video, we'll be discussing the binomial probability distribution. This is a continuation of the discrete random variable distribution, but we're going to become a little more specific. The binomial probability distribution is a discrete probability distribution that describes probabilities for experiments in which there are two disjoint outcomes. The following criteria must be met. 1. The experiment is performed a fixed number of times. Each repetition of the experiment is called a trial. For example, if I'm flipping a coin, each time I flip a coin, that is one trial. And I must specify at the beginning of the experiment how many trials I plan to do. For example, I say I'm going to flip the coin 20 times, so n is 20. Number 2. The trials are independent. This means that the outcome of the first trial will not affect the outcomes of the other trials. Back to the coin example, this is a good example of that. Whether or not I received a heads on the first trial does not affect the probability of heads on the second trial. Number 3. For each trial, there are two mutually exclusive or disjoint outcomes, success or failure. This is true for heads and tails since there are only two outcomes. Even if there are more than one outcomes, we can create a binomial distribution. For example, a dice that has 6 sides technically has 6 outcomes, but we can change the designation of the event we're looking for. Let's say we designate success as rolling a 1. Failure is rolling any other number. So that's two possible outcomes, success and failure, 1 or any other number. So we can create a binomial experiment by designating what you want to be a success versus failure being your two outcomes. Number 4, the probability of success is the same for each trial of the experiment. So for the coin example, you'd have a 50% chance of getting a heads each time. For the dice example, you'd have a 1/6 probability of rolling a 1 each time, and that number never changes. The following notation is commonly used. There are n independent trials, so how many times do you plan to flip the coin? P will denote the probability of success for each of the trials, so that clearly means then that 1 minus P is the probability of failure. Then let X denote the number of successes in n independent trials. So let's say I flip the coin 20 times, which is n, and I want exactly X, meaning 12 heads, so X would be 12. So the number of successes you want always has to be a number between 0 and the total number of trials. Let's do an example. First, let's state whether the following represents a binomial experiment. If it does, the probability is not a binomial experiment, and let's state why. In other words, does the response indicate only two possibilities? First question. A random sample of 15 college seniors is obtained, and the individuals selected are asked to state their ages. How many outcomes are there? Well, you're going to go up to the first college senior and you're going to ask him or her, what is your age? And if the response is only two possible outcomes, then this is a binomial experiment. However, when you ask this college senior what their age is, they could respond with 21, 22, 23, 24, whatever their age might be. So there's an unlimited number of choices for which the outcomes might result in. So no, this would not be a binomial discrete probability distribution because there are more than two outcomes. X can be any number ranging between 1 all the way up to infinity. An experimental drug is administered to 100 randomly selected individuals with the number of individuals responding favorably recorded. So again, you're administering a drug to 100 people. Let's just target one for now. So you administer this drug to an individual and you record whether they responded favorably or not favorably. So there are two possible outcomes. Did the drug work or did it not? Also, there are a fixed number of trials. You're only selecting 100 people, which is a fixed number of trials. In addition to that, the trials are independent from each other. Since whether one person felt favorable from responding to the drug does not have any effect on whether the next person might feel favorably. So those are independent. And the last one says the probability of success must be fixed, which we're assuming it is. Didn't really discuss the probability of success, but we're assuming it is the same for each individual. The third question says 100 randomly selected parents with at least one child under the age of 18 are surveyed and asked if they have ever spanked their child. The number of parents who have spanked their child is recorded. So the question is, I go up to a number of 100 selected parents. Let's say I go up to the first parent and I ask them, do you spank your child? There are two possible outcomes. They will either answer yes or they will answer no. So there are two outcomes. There's a fixed number of trials since I specified I'm only going to ask 100 parents. So I will not go over the 100 and I will not go under. It is a fixed number. The trials are all independent. Whether the first person said, yes, I spanked my child, does not have any effect on the probability that the second person might answer that they spanked their child. So the trials are, in fact, independent. Also, the probability is fixed. So the likelihood that the first parent will spank their child is going to be the same probability that the next person might spank their child. Now, the answers might be different, but the probability will not change. So the answer to this last question down here is yes, because of all the requirements aforementioned in the last example. We can also compute binomial probabilities 3 different ways. And for the first problem, we're going to do it one question 3 different ways, just so you can see how each of them relate to each other and how you can choose 3 different ways to do each problem. The first way you can do binomial distribution is you can do it by hand using this formula. We could also use what's called a table of probabilities, and we also can use statistical software such as StatCrunch. So the by hand formula is as follows. Although you will be provided tables on the exams and you will have StatCrunch available for your homework and your MyLab portion of the exam, make sure you can also do this by hand for the in-class exam. So the probability of obtaining X number of successes in n independent trials of a binomial experiment is given by the following formula. You're going to recognize parts of this. Back from Chapter 5, we learned what a combination was. This is a combination of n total trials. We're going to take X successes out of the n total number of trials. The next piece is the number of successes. So this piece right here, P is the probability of success. X is the number of successes we want. The last piece is 1 minus P. 1 minus P is the likelihood of failure. N minus X is how many failures you want. So for example, if I have 100 total trials and I'm specifically looking for 60 successes, so 60 successes at the probability of success, 100 minus 60 is 40, so I want 40 failures at the probability of what the failure rate would be. We could use the previous formulas to find the mean and standard deviation back from the first section in the first video of Chapter 6. However, there are some simpler ones that exist for using binomial random variables, and they are as follows. The mean is simply just n times p. And this actually is quite commonsensical. For example, if you have 100 people in a room, and you know 60% of them were going to have blue eyes, then 100 times 60% is 60, meaning you would expect 60 people to have blue eyes. So you're basically taking the probability of success times everybody in the room to give you the total probability of a success. This is the standard deviation of the random variable x. N times p, which is the probability of success, times 1 minus p, which is the probability of failure, all under the square root. So we can construct the binomial probability histograms as well. For example, when p is 0.5, we will have a symmetric distribution. So if you, like in a coin example, if you have a 50% chance of getting a heads and 50% chance of getting a tails, you'll end up with a symmetric distribution. Even with small samples. Skew starts to exist with small sample sizes when p starts to become much larger or smaller. So if p is a large number, or the likelihood of the probability of a success is maybe closer to 80%, you're going to have more of a skewed left graph. So this is when p is greater than 50%. If p is less than 50%, you're going to have more of a skewed right graph. So you're going to expect most of your data to be over here to the left-hand side, where the likelihood is going to be smaller than 50%, but you'll still have those outliers to the side. However, as the sample size begins to increase, the probability starts to become more bell-shaped. This result allows us to use what's called the empirical rule to identify unusual observations, provided that n times p times 1 minus p is greater than or equal to 10. So everything underneath this radical, this is what's called your variance. So if the variance, or everything underneath the square root of the standard deviation, if all of that is greater than or equal to 10, we can state that the empirical rule applies, and we state that anything outside two standard deviations from the mean is considered unusual. Secondly, we can use the tables, and we can also use StatCrunch, and I will run through an example of doing all three types for you next. So here, we have a binomial probability experiment, and we're going to conduct it with the given parameters. And let's compute the probability of x successes in the n independent trials of the experiment. And let's do this all three methods. So first, let's do all of these questions on this page using the formula. And then we'll do all of these again using the tables, and then we'll do them again using StatCrunch. So we'll do it three different ways. First, we'll use the formulas by hand. So this question is saying, I am going to do an experiment with 10 trials. So I'm going to do this experiment 10 times. I know there's a 40% chance likelihood that I'll end up with a success. And I want to know the likelihood that I'll get exactly 3 successes out of 10. Well, using the formula from the previous page, I know that I want to have the probability of getting exactly 3 successes, which is going to be equal to a combination of 10 total items, but I only want 3 successes, times the probability of success, and I want 3 successes, times the probability of failure, and I want 10 minus 3 successes. In other words, I want 7 failures total. So I would put all of this into my calculator, and you're going to get a value of 0.2150. So in my calculator, I'm going to do a combination of 10 items, taken 3 at a time, times the probability of success to the third power, times the probability of failure, which is the other 60%, to how many failures you want, which is 7. You're always going to notice that how many successes and how many failures you want have to add up to the total number that are in your trial. So we should get the same value here that I got by hand over here. So let's do the same thing a couple more times, again using our calculator, and then we'll move on and do these different ways as well. For this next example, I want an N of 9 total trials. I know the probability of success is 0.2. And this time I want to find the probability of getting 3 or less successes. So I'm looking for the probability of getting X, which is less than or equal to 3. Well, less than or equal to 3 entails 3 or less, so that it could include 2 successes, 1 success, and also 0 successes. So we individually have to find all the probabilities of each of these individually and then add them all together. So let's first find the probability of getting 0 successes. So the probability of getting exactly 0 successes, I will mimic what I did up here. So I want a combination of 0 successes out of 9 total trials times the probability of success, and I only want 0 of them, times the probability of failure, and I want all 9 failures, plus the probability of 1 success. So now we have to do all of this over again. So the probability now of 1 success is going to be 9 items taken 1 at a time. I want 1 success and 8 failures. Plus 2 successes will be next, which is 9 trials, 2 successes, which means then I'll have 7 failures, plus the probability of getting exactly 3 successes. So it's going to be 9 trials. I want 3 successes. That means I want 6 failures. So in my calculator, I have to add all of this up. It would be advantageous to do each individual part separately and add them all together. So that's what I did down here. I end up with 0.1342 plus 0.3020 plus 0.3020 plus 0.1762. And when I add those individual probabilities together, I get a total probability of 0.9144. So a 91% chance that I will select 3 or less successes out of 9 when each individual likelihood is 20% of succeeding. You can see that this becomes quite large when we have to do multiple of them together, which is going to prove to be a little grueling for this question. This question here says I have n independent trials, and I want to know the likelihood of getting 12 or more successes. So I want to find the probability of getting 12 or more successes. So we have to find the probability of 12 plus the probability of 13, 14, 15, and so on, all the way up to 20. So we would have to do this equation 9 different times and then add all those values together if we were to do this one by hand. I'm going to leave it here for you to go try on your own rather than waste the time in the video by using this method up here. If I wanted to set just this first one up for you, I would find a combination of 20 total items. I want 12 only successes. The probability of success is 70%. I want 12 successes. The probability of failure, and I want 8 failures. And then you'll have to do that all the way until you get all the way out to 20. And then you'll have to add all of those individual probabilities together. So this would be a good time to pause the video and then come back and see if you got the right answer. I got 0.8867. Now if you didn't get that answer, there's something probably wrong with the formula here, or more likely entering it into the calculator incorrectly. That's why it's good to have other methods for doing questions like this that get to be quite lengthy when doing it by hand. We'll check this answer using the tables in StatCrunch to see if we did it right. So if you didn't get this answer, we also have other methods. For the last one, when doing this by hand, we want to find the probability that x is between 10 and 12 inclusive. Which means x could be 10, x could be 11, and x could be 12. So this one wouldn't be too bad because there's only 3 possible outcomes that I need to add together. So the probability of getting exactly 10 successes is going to be a combination of n total items, which is 15, and I want 10 successes, times the probability of success, and I want 10 successes, times the probability of failure, and I want 5 failures. Then we're going to add that to the probability of getting 11 successes. So that's going to be 15 C11. I want 11 successes and 4 failures, plus the probability of getting exactly 12 successes. So that's going to be 15 C12, 12 successes, which means I'll be left with 3 failures. So when I put all of this into my calculator and I add all 3 probabilities up, you're going to get a total probability of 0.5026. So now what we're going to do is we're going to go back. Now we're going to do it a second way, which is using the tables, which for my class you will have access to these tables, which is a much faster way of getting to the same answers. Okay, so the tables that you will be given are also in your class under modules. Look for the tables at the very top for the course resources. But these binomial probability distribution tables are going to look similar to this. So at the top, you're going to have a probability of success, and down along the left-hand side, you're going to have the number of trials, and in the second column will be the number of successes that you want out of each of those individual trials. Okay? So for this first question that we have up here, we have a total of n trials, and we want exactly 3 successes. So we go back to our table and we look for n, which is 10. Okay, so we have an n of 10, and we want exactly 3 successes, which is right here, out of 10 total trials. Now we got to know which column we need to pick our probability from, and that comes from the probability of success. According to this question, the probability of success was listed as 0.4. So we go back to the table, we find the probability of success is 0.4, and where does that column meet this row? And the answer would be right here at 0.2150. So there's a 21% chance that you will select exactly 3 successes out of 10 if the likelihood of each individual success is 40%. And 0.2150 is the exact answer that I got here when I used the formula. See, all they did in the table was do all the math for you. So these tables are nothing more than somebody sitting around and generating all of these individual values. 0 successes, 1 success, 2 successes, 3 successes, all the way up to 10. So somebody did all the math for you and put all the values in a table so you can quickly reference them. Now, of course, these tables don't go up very high. The n eventually is going to end at probably 15 or 20 because the tables get quite long after that. So we'll provide the n all the way up to 15 or 20, but if n is larger, then you're stuck with either using the formula or statistical software. So let's look at the next example. The next example says my n is 9, and I want to find the probability that x is less than or equal to 3. So the probability that x is less than or equal to 3, we have to add all of these individual probabilities together. So when I go back to my table, I have to find each of these probabilities, and then I'm going to add them up, just like I did down here. So again, n is 9, probability of success is 0.2, x is less than or equal to 3. So in my table here, x is 9, or excuse me, the number of trials, n is 9. I want 3 or less successes. So that would be everywhere between 0, 1, 2, 3, and add those together. And I know the probability of success we said was 20%. So these are the values that I'm going to be adding together. 0.1342, 0.3020, 0.3020, and 0.1762. And you'll notice those 4 values are the same 4 values that we had in our lecture notes when we did it by hand. So you still have to manually add those together, which is what we did here. A shortcut to using this, by using table 3, which is what we're doing now, you could also use what's called table 4. Table 4 is a cumulative table. So if you keep flipping through your tables until you get to table 4, it's a cumulative table. It tells you what the probability is at a value or anything less than that. So if I switch over to table 4, you'll see that I have it now in table 4, which is the cumulative table. I go back to my n is 9, and then I look up a quantity, a total successes of 3, with a 20% likelihood of occurring. You're going to get 0.9144, which was the answer that we had on the previous problem, but this time I don't need to add them all up. It's already cumulative. It already took all the values from 0, 1, 2, and 3 and added them together to give you the cumulative value in table 4. So you don't have to do the math by adding them all together. Notice by the time I get to the bottom, they will all say 1 because you're adding up all of the individual probabilities together, which will always add up all the way to 1. Let's try the next one. Here we have a probability of success of 70%. We want to take n 20 items, and we want at least 12 successes, which means 12 or more. So 2 ways we can do this. We could go back to table 3 like we did for the first 2 examples, and we go to an n is 20. So here n is back in table 3. Here n is 20. And we want 12 or more successes. So that's going to be all of these added together. We know that the probability of success was 70%. So we're going to have to take this column all the way over here to 70%, which is all, this is this last column over here. So we're going to start with a 12 and 70%, which is starting here at 0.1144. And we're going to add all the way down to 0.0018. And when I add all of these values together, you're going to get the same value that you had in for your lecture notes, which should have came out to be 0.8867. So all of these values over here are all of the values of all of the individual probabilities listed here. And when you add up all of those individual probabilities, you're going to end up with 88.67%. Now the question is, can we also use Table 4? Table 4 is used for, again, for cumulative probabilities. So if we go back to Table 4 and we go to an n is 20, so again, here we've got Table 4, and down here we have n is 20. We want to find the probability that x is greater than or equal to 12. But unfortunately, this table only gives us values that are less than a number. Less than a number. So let's look at a number line just for a second. Here's 0, here's 20, and here's 12, right? I want to find the probability that x is at least 12. So that means 12 or anything more than 12 all the way up to 20. So it would include everything from 12, 13, 14, 15, all the way up to 20. And I would include all those values in my probability. However, Table 4 will only give us probabilities less than or to the left of a number. So if I could find this probability to the left of the orange line, if I can find this probability here, all I would need to do is take 1 minus that probability, and then that will get me the probability in the orange shaded area. So what I'm going to do is I'm going to actually look up the number 11 in this table, find the probability of something being at 11 or less, and then subtract that probability from 1, and that should give me the same value for the orange probability, which is to the right. So when I'm looking at my Table 4, at row 11, I go all the way over to the right-hand side to where the column where my probability of success is 70%, and I find this value right here, 0.1133. So this probability in this green shaded area is 0.1133. So the likelihood that something might be 12 or more is going to be the complement of that probability. So 1 minus 0.1133 is going to give me 0.8867. And when we go back to our lecture notes, you'll see that that actually was our answer. So Table 4 is nice, but it is a little tricky in reading it. Most students prefer to use Table 3, so they can just look at the individual probabilities and simply just add them together so they can make sure they're getting the right answer. Finally, for the last one, if we wanted to use the tables for the last one, here we have n is 15, and we have our probability, and we know our x needs to be between 10 and 12. So I would go to Table 3 and find each of these individual probabilities. So let's go to Table 3. N is 15, and x needs to be between 10 and 12. So here's Table 3. Here's n is 15. X needs to be between 10 and 12. And the probability of success was 0.65. So where do those meet? 0.2123, 0.1792, and 0.110. And when you add those three numbers together, you should get the same value that we had on our sheet over here, which was 0.5026. There are ways to use table 4 for this as well, but I'll let you try to investigate what those ways might be. Now we're going to switch over to StatCrunch. Okay, so now we're going to do the three examples back in StatCrunch. So the first one said we have an n of 10, probability of success of 0.4, and we want 3 successes. So we're going to go up to Stat. We're going to use the Binomial Calculator. All we have to do is enter in this data. This is going to look very similar to the discrete probability distribution we used before, but now instead of it automatically calculating what n and p is, you have to enter it in. Here we have n, we're going to use 10. We want a probability of success of 0.4, so we'll enter that in there. And we want x to be exactly 3 successes. So when we compute that, we'll get a probability of 0.2150, which is exactly what we have in the notes. The next question says we have n is 9. The probability of success is 0.2, and we want x to be less than or equal to 3. You see we have a probability of 0.9144. You can see how much faster it is to do them this way than it is by hand. For the third question, we have n is 20. We have a probability of success of 0.7, and we want to find the probability that x is going to be greater than or equal to 12. So we get a 0.8867, or 88.67% chance. And for the last one, we're going to go between two numbers, not greater than or less than one number. So we have to come up here and switch to between two numbers. N is 15. There's a 65% chance of being successful. We want x to be between 10 and 12 included. Notice that those are automatically included. You can't not include them. So if you didn't want to include 10, you would just change this number to 11. And when I compute, I get 0.5025, which is slightly rounded. We had 0.5026, so there might be a 10,000th of a number off there, probably with our rounding when we added the numbers together. For the last question, I'm going to do these all via the table. I'm going to give you a little bit of experience using the tables a little bit more, because that's likely how you'll be choosing to do those on the exam. The StatCrunch, obviously feel free to use that for doing your homework and for the online portion of your exam, but in class you're going to have to be utilizing the tables. And since it is faster than doing them using the formula, that's the way I'm going to show how to do these last few questions here. Certainly I would check your answers using StatCrunch and also doing the formula to verify that you're doing all of them the exact same way. Alright, so for the last question, it says, according to flightstats.com, American Airlines flights from Dallas to Chicago are on time 80% of the time. Suppose 15 flights are randomly selected and the number of on-time flights is then recorded. First, explain why this is a binomial experiment. Well, there's criteria that needs to be met, and you need to be able to state all the criteria. You need to have a number of fixed trials, and in this case we have 15 fixed trials. It specifically said we chose 15 flights. So we're not having any more or any less, and it's not dependent on our results. We're stopping at 15. Our trials have to be independent, which in case they are. If it doesn't state in the question, we'll assume that there is independence. We have two outcomes. The outcomes are on time or not. Lastly, we need to know that the probability of success is fixed, and it is. It's 0.8, 80% chance of being on time. So this is definitely a binomial experiment. So the part B says find and interpret the probability that exactly 10 flights are on time. So we already know what N is. We already know what P is. So we're going to go to our table, table 3, which is the one I'm going to use, and I want to find the probability of getting exactly 10 successes out of 15 if we know that there's an 80% likelihood of being successful. So I'm going to go to my table 3. I want N to be 15, and I want exactly 10 successes. I know the probability of being successful is 80%. So I need to follow this row all the way over until I see 80% over here. So where does that meet up? At 0.1032 over here. So the answer is going to be 0.1032. Let's try part C. Find and, oh, we didn't interpret. Let me go back. Got to answer the second question here. Find and interpret. If I were to interpret this question, I would say out of 15 flights, there is a 10% likelihood that exactly 10 flights will be on time. All right, part C. Let's find and interpret the probability that fewer than 10 flights will be on time. Question, is 10 included? If it says fewer than 10, that says to me that 10 is not included, so I will not put the underline there. Okay, so if I want fewer than 10, I'm going to go to table 4 and use my cumulative table. Now let's recall what fewer than 10 actually means. Okay, again, I'm going to go to my number line because this sometimes helps me in determining where to start. So I have 0 all the way up to 15, and here's 10. I'm asked to find the probability that fewer than 10 are on time. So that would be 0 all the way up to 10, but I'm not going to include 10. I'm actually going to stop at 9. So I need to find this probability in this orange area right here. So to find this probability, I'm going to go to table 4, and I want to find the probability between 0 and 9. So in table 4, remember my N is still 15. So here's table 4. My N is 15, and I want 0 to 9 successes. So I'm going to go all the way up to 9. I know the probability of success is 80%, which is over here. And when I follow 9 all the way across until I get to 80%, I find the probability is 0.0611, and that would include 9 all the way down to 0. It adds them all up for me. So the answer to this question is going to be 0.0611. Part D. Find and interpret the probability that between 8 and 10 flights inclusive are on time. So the probability X is between 8 and 10 inclusive. So that means we would include both of the endpoints. The easiest way to do this is use Table 3 and just find the individual probabilities of 8, 9, and 10. So I'm going to find the probability of 8, 9, and 10, and then just simply add them all together. So I'm going to go to Table 3 and find each of the individual probabilities. So when n is 15 in Table 3, I want to find the probability of being 8, 9, and 10 and add those three together. But make sure we find the 80% likelihood of success, which is over here. So we're going to add together 0.0138, 0.0430, and 0.1032. So we're going to add these three numbers together. And when you add those three numbers together, you're going to get 0.16. Part E, compute the mean and standard deviation of the random variable x, the number of on-time flights, and 100 trials of the probability experiment, and then interpret the mean. Well, we know by definition that the mean of a random variable x is simply just equal to n times p. Well, in this case, we're talking about 100 flights, and I know the probability that they will be on time is 80%. So I would expect 80 of the 100 flights to be on time. Standard deviation of the random variable x is going to be equal to square root of n times p times 1 minus p. N is 100, p is 0.8, 1 minus p is the probability of failure, which is 0.2. When you put this into your calculator, you're going to get 4 flights. So for the last question, it asks, would it be unusual to observe 75 on-time flights in this grouping of 100? Certainly 75 would be less than average, but is it enough less that it is considered unusual? Well, remember, unusual is going to be anything outside of 2 standard deviations. So if we know what a deviation is worth, we know anything would be unusual if it's more or less than 2 deviations away. So let's take the mean and let's subtract 2 deviations, or the mean, and we'll add 2 deviations and find out what that upper and that lower limit are going to be. So if the mean is 80 and I subtract 2 deviations or add 2 deviations, what will that lower and upper limit be? The lower limit will be 72 and the upper limit will be 88. And this is what we will call the usual range. I would expect to see between 72 to 88 on-time flights. This is the usual range because this is the middle 95% of the empirical curve. Anything outside of this range is the outside 5%, which would be considered unusual. 75 is in that range. So we would consider this a usual case. So no, it would not be unusual to observe 75 on-time flights, since 75 is in 2 deviations of the mean.